Quantum algorithms versus classical algorithms. The world of computing has always been defined by innovation, and recent decades have seen dramatic shifts in how data is processed and stored. From mechanical relays to transistor-based circuits, each evolution has unlocked unprecedented power and efficiency. However, the emergence of quantum computing threatens to redefine these boundaries entirely. This transformation is not merely a matter of faster processors or increased memory capacity. At its core lies the fundamental difference between classical bit-based computations and the probabilistic nature of quantum states. Understanding this distinction is critical for anyone navigating modern algorithm development or exploring cutting-edge computational science. The foundational principles of quantum computing. Classical algorithms operate on binary digits, bits, that exist in either a 0 or 1 state. In contrast, quantum algorithms leverage qubits, which can represent both 0 and 1 simultaneously thanks to the phenomenon known as superposition. This ability allows quantum computers to process vast amounts of information concurrently, making them ideal for solving complex mathematical problems. Superposition alone does not explain the full potential of quantum computing. Another vital principle is entanglement, wherein pairs of qubits become intrinsically linked so that the state of one instantly influences the other, regardless of distance. Entangled qubits form the basis for quantum teleportation and distributed quantum networks, offering revolutionary ways to share and manipulate data. Coincidence versus correlation. While classical systems rely on statistical coincidence to determine probabilities, quantum systems exploit deep correlations between particles to achieve deterministic results in probabilistic scenarios. Gates versus circuits. Unlike classical computers that use Boolean gates, quantum algorithms employ unitary transformations called quantum gates. These gates perform operations on qubits while preserving the total probability of all possible outcomes. Differences between classical and quantum approaches. In classical computing, data flows through a series of predefined steps that ultimately lead to a single solution path. Conversely, quantum algorithms explore multiple paths simultaneously, allowing for parallelism that fundamentally alters how problems are approached and solved. A central metric distinguishing these two paradigms is time complexity. Many classical algorithms exhibit polynomial time growth, O, n to the power of k, relative to input size, whereas quantum algorithms often reduce this significantly, achieving subpolynomial or even logarithmic complexities in select cases. The role of measurement. Making measurements in quantum systems collapses wave functions into definite states, a behavior absent in classical contexts. This collapse introduces inherent uncertainty when interpreting quantum results unless carefully managed through controlled observation strategies. Sometimes referred to as destructive testing, measurement must be applied strategically during execution phases to avoid prematurely discarding potentially valuable intermediate states held within entangled configurations. Pioneering quantum algorithms. Few individuals grasp the immense implications of quantum algorithms until they encounter pivotal contributions like Peter Shor's groundbreaking factoring algorithm. First introduced in 1994, his algorithm demonstrated that sufficiently powerful quantum machines could break widely used cryptographic protocols based on integer factorizations. Shor's achievement underscored the vulnerability of RSA encryption schemes upon which much digital security relies today. His approach relied heavily on modular exponentiation and period-finding properties enabled exclusively by quantum mechanics. Modular exponentiation, a primary building block in Shor's algorithm, involves calculating powers modulo n efficiently using quantum Fourier transforms. Error correction, despite being theoretically sound. Implementing such algorithms requires robust error detection/correction mechanisms given susceptibility to noise-induced errors prevalent in early-stage devices. Advantages of quantum algorithms beyond cryptanalysis. Quantum algorithms demonstrate remarkable versatility across domains ranging from combinatorial optimization to simulation tasks unfeasible within conventional frameworks. Their applicability spans industries including finance, logistics, materials science, and bioinformatics. For instance, Consider the traveling salesman problem, an NP-hard issue traditionally tackled heuristically by approximations. Quantum variants show promise toward yielding exact solutions exponentially faster than any known classical alternative under suitable conditions. Optimization through quantum annealing specialized versions of adiabatic quantum computing, notably D-Wave systems implementation of quantum annealing, target discrete optimization problems involving energy minimization landscapes. While still experimental, initial tests indicate potential improvements in finding near-optimal global minima. These implementations differ structurally from gate model quantum computers but highlight another avenue through which quantum-enhanced solutions manifest themselves practically outside academic labs. Current implementation challenges. Despite tremendous theoretical progress, translating quantum algorithms into functional hardware remains fraught with obstacles stemming primarily from technological maturity levels currently restricting widespread deployment efforts globally. Chief among these challenges is maintaining coherence times long enough to complete meaningful computations before environmental disturbances cause loss of quantum information, a challenge exacerbated by external magnetic field fluctuations and thermal vibrations affecting delicate superconducting loops hosting qubits. Decoherence, rapid decay rates limit actual computation durations, necessitating advanced cooling systems operating at millikelvin scales. Scalability issues. Connecting increasing numbers of qubits together without introducing additional interference represents one of the toughest engineering feats facing contemporary designers. Programming paradigms for quantum algorithms. Designing effective quantum software demands familiarity with unconventional coding styles unlike anything found within mainstream development ecosystems dominated by object-oriented or functional paradigms. Languages like Python combined with libraries such as Qiskit facilitate rapid prototyping while abstracting away many lower-layer concerns typically handled manually by seasoned physicists conducting theoretical studies. Hierarchical abstractions. Modern toolkits provide varying degrees of abstraction depending upon desired level of control. One might choose higher-level interfaces resembling pseudocode structures versus diving straight into circuit definitions composed purely out of fundamental gates. Simulation tools. Before executing costly real hardware trials, cloud platforms allow extensive virtual experimentation enabling cost-effective refinement prior committing resources permanently. Educational resources and communities. As interest grows among programmers eager to understand how these novel algorithms function, educational initiatives flourish providing access through online courses, interactive simulators, and vibrant open-source communities contributing actively maintained repositories filled with ready-to-run demonstrations. Communities spanning GitHub forums along with Discord channels host active discussions revolving around latest publications appearing weekly in journals devoted strictly to quantum computing research themes. Hands-on learning platforms. Websites offering sandbox environments where users can experiment safely without risking damage provide invaluable learning opportunities particularly beneficial beginners unfamiliar with arcane aspects governing underlying physics phenomena. Such platforms expose students gradually moving progressively from basic arithmetic exercises up towards designing entire quantum circuits targeting specific objectives such as implementing simple oracle functions behind Grover search mechanism. Future prospects and research directions. While present-day implementations remain rudimentary, ongoing R&D promises substantial improvements forecasted to unfold steadily over ensuing years, perhaps even sooner than many anticipate. As companies invest billions annually chasing dominance within burgeoning markets expecting eventual adoption waves once sufficient infrastructure matures adequately. Emerging directions include pursuit of universal fault tolerance capable of correcting arbitrary errors spontaneously thereby eliminating reliance solely upon painstaking manual verification processes previously necessary for ensuring reliability standards comparable those achieved within classical digital electronics industry benchmarks. Topological qubits. Researchers investigate topologically protected qubit designs resistant naturally occurring defects leading promising prospects towards stable storage duration requirements. Photonic implementations. Alternative photonic approaches employing light photons offer advantages concerning transportation speed, facilitating network connectivity enhancements impossible currently achievable utilizing electrically driven microwave resonators employed prevalently nowadays. Implications across industries, across sectors relying extensively upon predictive analytics, from stock trading floors to climate modeling centers. The arrival of viable quantum hardware stands poised to revolutionize operations, substantially transforming everyday decision-making routines undertaken routinely worldwide daily. Healthcare providers working closely with pharmaceutical firms may soon witness accelerated timelines associated with drug discovery cycles, reducing costs dramatically, permitting quicker availability, life-saving treatments benefiting millions. Suffering ailments previously considered untreatable indefinitely due prohibitive financial constraints limiting clinical trial scope. Drug discovery acceleration. Simulating interactions between molecules computationally enables identification candidates worthy further investigation, drastically cutting expenses incurred during traditional wet lab experimentation stages, typically consuming majority available budgets allocated R&D departments. Cryptographic security reinvention. Organizations tasked securing sensitive communications begin evaluating post-quantum cryptographic standards, proactively preparing contingency plans, mitigating risks posed, imminent obsolescence, outdated public key infrastructures threatened, vulnerabilities exploited, potent decryption capabilities promised upcoming generation quantum-enabled adversaries. Concluding thoughts on quantum evolution, reflecting back, reveals profound journey traversed, examining nuances distinguishing classical versus quantum computational worlds, emphasizing striking disparities rooted deepest architectural principles guiding design choices, influencing resulting performance characteristics, exhibited final output behaviors. Taking everything accounted, we stand at inflection moment, history witnessing transition phase, accelerating toward realization, tangible benefits derived, harnessing newfound capabilities previously confined, theoretical realms reserved, academic scholars pondering implications, hypothetical scenarios envisioning alternate realities shaped, radically divergent trajectories arising from technological revolutions unfolding continuously around us every day.